Welcome to this brief introduction to structural equation modeling with IBM SPSS AMOS. AMOS is a fairly well-established structural equation modeling or SEM software package. And it's actually an acronym that stands for Analysis of Moment Structures, which is a type of SEM analysis. AMOS is sold as a standalone package as well as an SPSS add-on module, and it's especially useful for analysts who are interested in things like path analysis and confirmatory factor analysis, of which we'll see an example later. It's also known as analysis of covariance or sometimes causal modeling software. These are all terms that are associated with structural equation modeling. Now, structural equation models actually encompass many modeling procedures that are already familiar to statisticians and are certainly available in packages like SPSS Statistics, because they encompass the entire catalogue of what are known as general linear models. And that means that they do everything from t-tests to correlation analysis to linear regression to factor analysis to complex ANOVAs. SEM allows these techniques, in fact, to be expanded into a richer set of analytical capabilities and to develop more complex causal models. It enables analysts to specify, estimate, and assess models showing hypothesized relationships in a very visual format. The software is very popular for researchers wishing to specify and test things like attitudinal or behavioral models reflecting complex relationships. The IBM SPSS Statistics Premium Bundle package actually includes the AMOS software. So if you've got IBM SPSS Statistics Premium, you've already got AMOS. Let's take a look at it. So here we are in AMOS, and just to show you what version I'm working with here, I'm working with version 27, that's the build number. And if you've never seen this software before, what you first notice when you open it up is that you get this white portrait page here. This is in fact the worksheet that you're going to build a structural equation model on, or your path if you like. You're going to specify the model here using these various symbols and connectors. I don't find it terribly intuitive to have it in portrait format. A lot of people like to work in portrait format. I prefer to work in landscape format. So if I go to view here, interface properties, I can switch this to landscape A4 and then it'll just switch that. I can use my middle mouse button to zoom in or out. And what I want to do is just demonstrate how you can do a really simple linear model, a linear regression if you like, exactly the same sort of thing that you would get in SPSS. If you're not familiar with linear regression, you want a little introduction to that, just Google Smart Vision Introduction to Linear Regression and you should get a video that we've done on this previously, which will give you a good primer on that. To begin with though, I want to open up some data and I'm going to bring in an SPSS data file here. To do that, if I go to File, what I mustn't do is click Open. Open will actually open up a AMOS worksheet or an AMOS project file, which are given the extension .amw here. Rather, I'm actually going to bring in a data file. So if I click on Data Files here and go to File Name, and then I'm going to choose a data file that's familiar to people who are working with SPSS sample data beforehand. It's the employee data file. I've just added the field age in there. So the employee data file is, I'm going to open that, click OK, and you don't really see it here, but if I click on this little button, it shows me the list of the variables in the data set. And there are variables in the data set. Now, if I want to build my regression model, I need to specify, of course, a dependent variable, a target field, and some independent or predictor fields. And normally within packages like SPSS, you have a little dialog box where you send the dependent to one box and you send the independents to the other box. So it's very rigid. You know, there's a lot of sort of deviation around that. With structural equation modeling, things are a lot more sort of free form, but we can do a basic linear model here. One way in which I could do that is simply by drawing out a little box here for an observed variable. So I could put an observed variable in that and tell it the name of the field I want to go in there. I don't need to do that. I can actually just click on one of these fields here, like salary, which is current salary, and I can drag that and it just pops it on there. So it's done it already for me. It's identical to drawing an observed variable. Now the rectangles themselves are not just aesthetic properties, they actually represent the fact that it is a physical field in a data set, whereas a oval shaped object like this represents an unobserved variable, usually a latent field or latent variable, like that you would create through something like factor analysis or principal components analysis. So it's a latent field. So it's a construct, if you like, of the data. Here we're working purely with observed variables, and if I want to, say, predict or estimate current salary using things like beginning salary, then put beginning salary here and just drag that out. And I can add in things like their previous experience, which I can add in here. And I can add in things like their education. Let's just go for 3 fields, education, like that. So the next thing I need to be familiar with is, having specified these, is I need to be able to connect them up in some way. So I can use this sort of regression line here. This is a draw path, a single arrow path. Just means I'm using this to predict this, using this field to predict this field, this field to predict this field. Okay. And if I click on my little move objects button here, this little truck button that allows me to move objects around. Now, it's actually necessary within structural equation modeling packages, and AMOS is no different, to specify what's called an error term for a dependent field. So you usually have at least one field that has an error term associated with it. And once you've done that, you actually need to give the error term a name. So it's convention to give it like something like E1 or something like that. That's basically what's left over, or when you've tried to predict this outcome. You know, what is the error, if you like, in that variable. It's also quite common for people to actually look at what are called covariances, which are the relationships between these fields here. Don't worry too much about the fact that these arrows are kind of a little bit messy here. So here I'm going to go here to this one. So this is kind of like the correlations, if you like, between the independent fields. You got a little button here called touch up, which allows you to touch up the fields. So if you just click on these, it just allows you to clean them up a little bit, so you can see the covariances. So it just lets you all clean it all up a little bit. And you can also move things around, of course, if you don't like where they are. If you want to select groups of them, you can click on this button here and select groups of them, and then click the move button, if you like, to move them all around. So you can move them all around one group. So there's a lot of this sort of playing around with single selection, selecting all objects, moving them around, zooming in or out. And it's necessary to get used to dealing with those, I guess, if you're going to make sense of the analysis as you're going along. So this is the basic structure here that we've got for this particular analysis. If I want to specify the analysis that I want to run, I can go to analysis properties here. And you can see here that it gives you different types of estimation. So you've got things like maximum likelihood and generalized z-squares. It's one of the reasons why people like working with structural equation modeling software, is because they get different sort of estimation algorithms. Something that's important to be aware of is, if you have missing data, you'll need to check this button here, which is estimate means and intercepts. If you've got missing data, I don't think I've got missing data in this data set. I think it's complete, but if you have, you may find you get a warning message telling you need to estimate means and intercepts, and that's referring to this button here. But if I go into this sort of analysis here and go through these different outputs, I can say, okay, I want standardized outputs and I want multiple correlations. That should do for that. Just be aware that you can also do bootstrapping in here. It's quite useful to know about. And you've got stuff about permutations and random seeds, if you're working random seeds, and you can give it a title, etc. Now, if you want to run the analysis, you're going to click this button, which is calculate estimates. And when I do that, it says, okay, give me a name for this. I'm just going to call this linear. I'm just putting it in the temp folder here. So put linear and hit save. And it does the analysis. And as you can see here, we've got some big numbers here. These are the actual raw values, if you like, for salary and for the variance and the covariance for a salary. So if I click to standardized estimates, it's actually really showing me the regression weights, if you like. So I can see here that we've got a pretty good R-square value here. This is effectively a loading, if you like, or a beta calculation, if you prefer that term, a loading. 0.8 here is quite a good R-square. We can see that previous experience in month is very weak here. It's actually got a minus 0.1, so it's actually saying the more previous experience you have in months, the less your salary is. And then education level is also fairly weakish at 0.12. Beginning salary, of course, is the strongest relationship between this and current salary. And then we've got the the actual relationships between beginning salary and previous experience in months, which is again very weak, an education level in years, and previous experience, which is kind of medium negative, 0.25 here. And then quite a strong relationship between beginning salary and education levels in the year, coming out at 0.63. You don't have to just read off these values using the unstandardized or standardized estimates. You can actually see the output as it's shown in the view text button here. And then, of course, it's going to give me a lot more information about the analysis itself. So we can go down to, for example, the estimates here. The estimates table, if I just make that, maximize that, you see, for example, you have the estimates themselves, which this is akin to the coefficients table that you would get in a linear regression analysis. So we can see that the relationship between salary and beginning salary, every unit of beginning salary is worth $1.75 in current salary, and that is statistically significant. If anything, previous experience for every 16, I assume that's in months, every extra month of previous experience means you earn $16 less. It is actually statistically significant. And education is worth $733 for every 1 unit increase in education, which is also statistically significant. If you're wondering why previous experience actually affects your salary negatively, it's because a lot of the most poorly paid people in the organization are people who are older and who are working in a custodial role. So they have a lot of previous experience, but they tend to earn less. So as a result of that, it tends to have a negative effect. And then we have the regression weights themselves, which is just basically, if you like, a sort of correlation or a loading between beginning salary and previous experience, exactly what we saw earlier on in the chart. We have covariance analysis here, which is the relationship between the independent variables, which is previous experience, and salary beginning, which is technically beginning salary, which is technically not significant, but there is a significant relationship between previous experience and education, and between beginning salary and education. And then we have correlation values here, which are showing quite strong relationships here, for example, between beginning salary and education, but very weak relationship between beginning salary and previous experience. And then we have effectively a table of variances. This is kind of like an ANOVA table here, which is just, instead of showing you the standard deviation, it's showing you actual variance of beginning salary. And they're all statistically significant before finally we get our kind of R-square value here of 0.8 for the salary field itself, which is reflected here in the diagram. So that example served as a good introduction to structural equation modeling and AMOS in particular, because it allowed us to reproduce the type of analysis, very simple analysis, that we would do in, say, something like SPSS statistics, where we have a dependent field and a number of independent fields, and we used to model the relationships between them using, for example, a linear model. In the current diagram, we can see how we can extend the functionality of AMOS and structural equation modeling so that we can model more complex interrelationships, whereas in packages like SPSS statistics, the relationships are almost predefined. We have a dependent box. We have a set of independents. We don't really have the opportunity to model the interrelationships between them in a sort of customized way. Here, it might be argued, for example, that beginning salary is in many ways a function of your education level in years and your previous experience in months, since that dictates your starting salary. And then your current salary is really related to your beginning salary and the months that you've been in the job. And thus we can start to define more complex interrelationships. So we say, well, if we wanted to just predict beginning salary using previous experience in months and education level in years, how well would we do that? 0.45 here. And if we wanted to use all 4 of these fields to predict current salary, how well would we do that? 0.81. And we can just basically go to town a little bit and start to look at these interactions in a much more complex manner. In the next example, we're going to look at a classic structural equation modeling task, which is confirmatory factor analysis.